Brent from Michigan State University. He's going to speak about the free Stein dimension.
Thank you very much. Thanks to the organizers for this opportunity to speak. So this is based on joint work with Ian Charlesworth that we put on the archive beginning of this year. So throughout this talk, I'm always going to have some star algebra A and equipped with a faithful tracial state tau. So A will be, in fact, a finitely generated unidal star algebra. And tau is going to be a faithful tracial state. And the idea is I want to associate to this data some number, some numerical invariant, which will be called the free Stein dimension. And we'll see that it's sort of similar in spirit to this free entropy dimension that came up in Dan's talk. It'll share a lot of properties, and it's a little bit more closely related to its so-called non-microstates cousin, which you'll possibly see in Dima's talk later in the week. But so the idea is I want to extract some number from this information, and the goal of doing that is that hopefully this number then tells you some information about this algebra, or more generally about some von Neumann algebras or C-star algebras associated to it. So given this data, I can first of all consider the GNS Hilbert space associated to it, and I'll denote that by L2 of A tau. And because tau is faithful, I can identify A as living inside the bounded operators in here. And then I can also complete A to a von Neumann algebra by taking its double commutant. So if you like, you can always sort of think of your data as already starting as living inside some von Neumann algebra that's generated by this star algebra A, and it comes equipped with a trace. Now, we'll mainly be interested in derivations on this algebra, which I'll denote by der A tau. So these are derivations from A into a certain Hilbert space, namely A tensor A op with respect to tau tensor tau op derivations. And what I mean by a derivation is it's a linear map on A that satisfies the Leibniz rule. So delta of xy should be x dot delta of y plus delta of x dot y, where here this left action by x and this right action by y are determined as follows. Inside of this Hilbert space, I have densely spanned by elementary tensors like this. And so when I multiply on the left by x or on the right by y, what I mean is look at xa tensor by. And the circ here is denoting op, which means it's the same algebra, just equipped with the opposite multiplication. And in light of that, you can equivalently think of this as x tensor y op times A tensor B op. So the op is serving the purpose of sort of reversing the multiplication of that second factor and making it a more honest right action. Okay, so these are the kinds of derivations that we'll be interested in. And typically I'm going to actually mute this notation of taus just because we'll use the same trace throughout. So there shouldn't be any ambiguity. And one always has a rich source of examples coming from what are called inner derivations. Namely, if I take some vector C inside of this Hilbert space, then I can define a derivation by taking its commutator. And I'll let you check that this satisfies the Leibniz rule with respect to these relations. And let's write from now on in der is the space of all inner derivations associated to such vectors. So in certain contexts, these are the only derivations you get, but we're kind of interested when there's more, but this is at least a nice foundation of derivations that we'll be using. And I want to point out an important property that these have, which we'll be interested in a couple of minutes. So let's consider the case when C is a simple vector of one of these elementary tensors, A tensor B. And let's look at what happens when we plug its output against some element of the algebra X against the specific vector 1 tensor 1. So using this action, what I can do is move this copy of A tensor B over into the right coordinate. Let's use this fact that I have a trace. Never mind. And then I can reduce this inner product, which is occurring on this tensor product of Hilbert spaces, to now occurring just on a single Hilbert space. I get something like this. A star tau of B star minus tau of A star B star. And so what we've really shown here in this computation is that if I view this derivation, let's call it delta. If I view this derivation as a densely defined map from L2 of A into L2 of A tensor A, what I've shown is that 1 tensor 1 is in the domain of its adjoint, thought of as a linear operator going in the other direction. Okay. And moreover, we know what its image is. It's going to be precisely this. So delta star of 1 tensor 1 is given by A star tau B star minus tau of A star B star. And well, we did this for an elementary tensor, but there's nothing stopping you from doing this for a generic vector in L2 of A. So in fact, all inner derivations satisfy this property that 1 tensor 1 is contained in the domain of their adjoint, and we can say precisely what their image is. And well, the reason why we're going to care about this is because effectively this is going to give us sort of the next best thing to continuity in this context. So based on this computation, let's define der 1 tensor 1 to be all the derivations, not just the inner ones, so that 1 tensor 1 is in the domain of their adjoints. Okay, and specifically, this class of derivations is what we'll be interested in and what is going to allow us to make to define this free Stein dimension. Okay, so at this point, I've really only done algebra, and I guess I should point out that this example tells us that this always contains the inner derivations and potentially more. But so let's maybe involve a little bit of analysis here. So one of the assumptions I had made about this algebra A, which I haven't used yet, was that it was finitely generated. I'll use that now. So take some subset X, which is self-adjoint and finite in A, so that it generates A as an algebra, meaning every element in A is some polynomial in the elements in X's. So I can then use this set X to define a map from derivations into a direct sum of this Hilbert space, direct sum size of H, say, where I send a derivation and I map it to its values on the X's in this set. Okay. Well, since the X's generate A as an algebra, that in particular means that monomials in these things are dense in A, span A. And because the derivations satisfy the Leibniz rule, what this tells you is that actually these values uniquely determine the derivation delta. So in fact, this is an injection. I can recover a derivation just from knowing what it does on these generators. And now I'm going from some kind of abstract space of derivations into a concrete Hilbert space. And importantly, this Hilbert space admits a right action of the von Neumann algebra generated by A tensor A. Double commutant here. Okay. So, well, without the direct sum, this thing acts on the left and right just by left and right multiplication that extends to this GNS Hilbert space. And then when you take direct sums, you just allow the action to be diagonal, so act the same on all the coordinates. And one thing you can check was that, well, my Leibniz rule here involved left multiplication by X and Y. And here, this uses right multiplication. So this action doesn't interfere with the Leibniz rule at all. And what that tells you is that whatever the image of this derivation space is under this map, it will be invariant under this action. So this gives you some subspace, and you can check that it's closed. Pointwise limits of things satisfying the Leibniz rule, You can check that it's closed and it's invariant under this action. And what that means is that you can look at its von Neumann dimension. So for K, a subspace of derivations, and I'll write this subscript A tensor A double prime to mean that it's closed under this induced right action. You can define a dimension of these things to be their von Neumann dimension as a right A tensor A module, rather their image. So delta X, X and X, delta and K. More precisely, what it means to be invariant in this right action is that it corresponds to some projection coming from n by n matrices over A tensor A double prime, and you can define a trace of that, and that gives you this number in particular. Something else I wanted to say here. Right. Now, you might be worried that this depends on this choice of generating set X. But fortunately, since the generating set is finite, what you can show is if you had some other generating set for A, well, then that means that anything in X, you can, let's say you had another generating set Y. Well, then any element of Y you can write as a polynomial of X's and vice versa. And then more or less the chain rule tells you that you between the image you get by applying these things to the X's versus the Y's, these are isomorphic as right module maps, and in particular the dimension is preserved. So moral of the story is that chain rule tells you that this thing does not actually depend on your choice of generators X. Okay? So it still just depends on this particular algebra. And then as an example, you can check that the inner derivations are a right A tensor A module, and so they have some dimension, and it's given by the following quantity: 1 minus the dimension of the, let me just write, A central vectors in L2 of A. So these are the vectors C, so that X dot C equals C dot X for all X and A. And why does this make sense? Well, because if you had such a vector and then you attempted to define a derivation with it, the fact that these two are equal tells you that their derivation is just constantly 0 on the algebra A. So you would expect these things to not really contribute as derivations, and so that's why you subtract off what their dimension is. And then otherwise, 1 is the dimension of L2 of A tensor A itself. And there are nice cases when you know that this this dimension is actually 0, namely if A generates a diffuse von Neumann algebra, then that will just always be 1. Okay. So coming back to this this space of derivations here, I want to define the free Stein dimension as the dimension of this space of derivations, but there's a couple of issues. One is that this may not be closed. Its image under this mapping here may not be closed. Well, okay, that's fine. We can take a closure. That's not a big deal. The bigger issue is that we don't know a priori that this thing is invariant under the right action of A tensor A double prime. But fortunately, Voiculescu did a computation which saves us. So I'm taking some liberties with how this is being phrased, but this is more or less a computation that appears in one of Dan's papers. So for X and Y in our algebra A, and some derivation in the special class, 0, 1 tensor 1, it turns out that X tensor Y is in the domain of the adjoint and is given by the following. following product. And M here is the multiplication map where you take this tensor product and just multiply everything together. Okay, and this is a pretty straightforward computation if you just check things in terms of inner products. But for our purposes, there's two important consequences. So the first is that this tells us in particular that the entire algebra, A tensor AOP, lives in the domain of delta star. And if you view this as some subspace of this L2 space, it's in particular dense. And so therefore this delta star, this adjoint, is densely defined. Okay. And if there's one fact that you know about unbounded operators, it's that an unbounded operator is closable if only its domain is densely defined. So you get that delta is what's called closable. And so, typically derivations are unbounded. Think about the usual derivation from calculus. It's not going to be bounded. So the next best thing you could hope for is to be closable. This gives you some kind of semblance of continuity in this unbounded case. And so here we have that for these derivations. And that's ultimately why I demanded that one tensor one was in the domain here. And then the other important consequence is that this also tells you that if you restrict the right action to just the algebra A tensor A, not necessarily the von Neumann algebra, that this space of derivations is invariant, and this is sort of saying what the new image of one tensor one of the adjoint would be. Okay, but we need it to be invariant under the von Neumann algebra generated by that. But like Kaplansky density theorem, if you take the closure, then you'll get invariance under the von Neumann algebra. So now this gives me some subspace that I can associate one of these dimensions to, and that's what I'll call the free Stein dimension. Stein dimension of this pair, A tau, is, I'll write it as sigma of A tau. This is the dimension of the closure of this space of derivations. Okay. This will be a number between 0 and the size of a generating set. So if your algebra, say, is singly generated as an algebra, then it'll be 0 and 1, but it can be larger. And in fact, it can take any value between 0 and infinity. Yes. So, okay, so there's this quantity. And I think one of the main selling points of this quantity, although perhaps it's not apparent from what we've done here, is that it's actually relatively easy to compute. So let me give you some examples to try and convince you of this. So the first are finite dimensional algebras, which are related to the matrix algebras that Jamie just mentioned. So if A is finite dimensional, then, well, linear maps on finite dimensional spaces are automatically bounded. And it turns out for derivations, bounded is equivalent to being inner. So in fact, all derivations are given by the inner ones. And in particular, then our special class der1 tensor 1 will also always be given by these inner ones. And well, so then sigma of A in this case is the dimension of the inner derivations, we computed here. And it's 1 minus the dimension of the A central vectors. But more explicitly, if you say look at the n by n matrices with their usual normalized trace, then it turns out that the A central vectors in that context have dimension 1 over n squared. Or equivalently, this is 1 minus 1 over the dimension of the algebra. So in fact, this agrees exactly with this topological free dimension that Dan was talking about in his talk. Okay, next we can consider, say, A is the algebra generated by a single self-adjoint operator, say with spectral measure μx with respect to tau. So this is precisely the distribution that Hari was mentioning in his talk. Then in this case, the free Stein dimension is given by 1 minus sum over t real numbers, μx, and the measure of a singleton t squared. So for most values of t, that expression will be 0. This thing is just looking through R to find any atoms for the spectral measure, and then subtracting off their square from 1. So in particular, if the spectral measure is diffuse, if it has no atoms, then this sum will be 0, and you'll just get 1. So for the commutative examples, we understand this pretty well. I'll say more about that in a minute. Okay, so using some work of Mineev and Shevchenko, 2005. You can compute this thing when you take gamma discrete group. You can consider as an algebra the group algebra, C of gamma, with the usual trace that constant element gamma is 0 unless it's the identity group element, in which case you get 1. And what you get here is some formula in terms of what are called the L2 Betti numbers. Beta 1 gamma minus beta 0 gamma plus 1. And if you don't know what those are, maybe a more enticing formula here is to just write the free entropy dimension of the group algebra. Okay. And this is really what Mineev and Shevchenko did. They showed that the non-microstate's free entropy dimension was given by this formula, and we can show that we get the same quantity for this free Stein dimension. Okay, so this gives you some interesting quantity related to groups. In particular, if gamma is infinite, then this beta 0 will be 0, and then beta 1. Well, the value of that is of a lot of interest in examples in von Neumann algebras. Let me maybe not say more than that here. And then we have some sort of more traditional free probability examples. So say you've got x1 through xn are free semicircular. So they're freely independent, and their individual distributions are that of a semicircle law. Then the free Stein dimension of the algebra they generate going to be precisely n. And it's important to note that the von Neumann algebra generated by these variables is the group von Neumann algebra for the free group factor on n generators. Well, we have generalizations of these things for non-integer n. This is due to work, sort of parallel work by Ken Dykema and Radulescu. And so using work due to Mike Hartglass and myself from 2018, what we show is that for all t bigger than or equal to 1, you can find some star subalgebra A in the interpolated free group factor that generates it as a von Neumann algebra, weakly dense, whose free Stein dimension gives you this parameter t. Okay. So in particular, you get every value from 1 to infinity. And to get anything between 0 and 1, you can play around with examples. Okay. So we have lots of examples of these, and I suspect there's more examples lurking out there. In particular, for things like hop star algebras and quantum groups, I think that you can probably compute this. You can probably compute this quantity for a lot of their standard generators. We do that for the free orthogonal quantum group, but I don't want to define what that means, so I won't write anything. Okay, so let me tell you some properties of this thing. This is due to Ian and myself. This here. Okay, so the first is that, you know, if it's some dimension quantity, you would hope to have some kind of additivity or subadditivity, and you do indeed get that. So if you take 2 star algebras A and B, and you look at the star algebra that they generate together, so this is assuming that they're already living in some larger algebra with some specified position, free or commutative or something like this. But you can consider this, and it's always bounded by their individual, the sum of their individual free Stein dimensions. And moreover, you get that these will actually be an equality if A and B are in free position. A, free, B, with respect to this trace tau, free in the sense that Hari defined. So this thing interacts nicely with free independence, and in particular, that's how you can compute this example 4. You just get the sum of the individual free Stein dimensions. And since the semicircle distributions don't have any atoms, for each one of them, you'll get a 1 in this computation. We also know how this thing interacts with direct sums. So necessarily on direct sum, your trace on the algebra is some convex combination of the traces on A and B. And that's going to factor into this formula. So you get trace of the identity for A squared, sigma of B, plus sigma of A, trace for the identity of B squared, plus some other term, plus 2 times the product of the trace. Okay, and if you've worked with these free dimension quantities enough, this is sort of the expected formula, so nothing super surprising there. We also know how it interacts with tensor products, at least for finite dimensional tensor products. E needs to be finite dimensional here. So then you get sigma A plus sigma B minus their product. Right. So those are all the sort of algebraic conditions. Now say you're looking at an algebra generated by some, say, self-adjoint operators, x1 through xn. Then you can compare this to the non-microstates free entropy dimension, which hopefully you'll see a definition of later in the week. And you can always compare them. So in particular, this is always less than or equal to this, And in fact, whenever these two quantities can be computed, you actually get equality. So it could be that, in fact, this is always equal to this thing. That would be a fantastic theorem to prove. I'm not sure it's true or not, but it's worth trying. So for those of you who know what this dimension is, there you go. Another important fact here is that if the von Neumann algebra generated by A is diffuse, then this guarantees that the free Stein dimension for A has to be at least 1. And what's going on here is just that when this von Neumann algebra is diffuse, that prevents this L2 of A tensor A from having any acentral vectors. And so consequently, for a lower bound for this, you can always just look at what the dimension of the inner derivations is. And if there's no acentral vectors, then that's always at least 1. And then lastly, last property I'll mention here. So if you make use of some work due to Dabrowski from 2010. So say there exists some generating set, finite generating set for A, generates A as a star algebra. And so that the free Stein dimension of A is maximized in the sense that it's equal to the size of this generating set. Then what you get is that the von Neumann algebra here is necessarily a factor. So from this quantity, you can detect structural information about this von Neumann algebra, things like factoriality. And conversely, structural information about the von Neumann algebra can tell you information about this quantity. So these are the types of theorems I'm interested in around this quantity. When can you deduce information about this von Neumann algebra A double prime based on values of this free Stein dimension? Then there's the big lurking question about this. Yeah. Here. I might have gotten my terms mixed up. Ah, yes, you're right. Sorry. This should be A and this should be B. Trace of A is pairs. Okay, so the big question related to this quantity is, suppose you had two star algebras, A and B, that generate the same von Neumann algebra. Does that imply that their free Stein dimensions are equal? Okay. Well, from this example with these free semicirculars, since it's plucking out this number n, if this was true, then you would be able to resolve the free group factor isomorphism. So what that means is this is probably a very difficult, if not impossible, question to answer. So a more modest question is then, for what von Neumann algebras A double prime does this hold? So whenever this holds, what you're really saying is that this sigma of A, it's not just an invariant of the star algebra A, but rather an invariant of the von Neumann algebra it generates. So I want to know, for what von Neumann algebras is the free Stein dimension an invariant of the von Neumann algebra? And well, a sort of initial example, which is pretty stupid, is if A is finite dimensional, then it's already equal to its own von Neumann algebra. Since it's an invariant of the algebra, it's an invariant of the von Neumann algebra. So great. So there's our first example that says yes to this question. Okay, well, you might want an infinite dimensional example. And if you work a little bit, you can get something for separable abelian von Neumann algebras. So this is due to Ian and me. So if M is a separable abelian von Neumann algebra with minimal projections E. Then for any star algebra that generates this, you're always going to get the same value for the free Stein dimension. And for any A and M, A double prime equal to M, free Stein dimension is going to be 1 minus the sum over projections in this set P, tau P squared. And so this should remind you of that one variable example when I considered the algebra generated by a single self-adjoint variable, and I got 1 minus the squares of the masses of its atoms with respect to its spectral distribution. So this is just saying this when potentially you're viewing that abelian algebra as generated by more than one variable. So here's another class of von Neumann algebras for which this thing is an invariant. So after these two examples, well, we have all the finite dimensional things, and now we've got an infinite dimensional thing, but it's commutative. So you want now some infinite dimensional von Neumann algebra that's non-commutative. And the first natural one to consider is the hyperfinite 2-1 factor, which we don't have a result for, but I'll make a conjecture. So if A double prime is equal to R, the hyperfinite 2-1 factor, then I claim that its free Stein dimension should just always give you 1. And so what's the intuition behind this? Well, here's a very crude definition of the hyperfinite 2-1 factor. You can think of it as some kind of limit of matrix algebras as the size of the matrix goes to infinity. If you've seen the construction of this, this is not too dishonest. But well, so if it's a limit of matrix algebras, then you would expect that its free Stein dimension for some generating algebra should be the limit of the corresponding free Stein dimension for the matrix algebras. And this was one of my examples earlier. For that, we got 1 minus 1 over n squared. So the limit is indeed 1. Some more compelling evidence for this is that if you take gamma to be an ICC, infinite conjugacy class, amenable group, then in particular, due to this work of Kahn from '76, you get that its group von Neumann algebra is necessarily isomorphic to the hyperfinite 2-1 factor. And well, we have some examples where we compute the free Stein dimension of a dense subalgebra here, namely the group algebra. This gave me some formula in terms of these L2 Betty numbers. And well, without going into too much detail, that formula will always give you 1 if you have an infinite amenable group. So we have lots of examples of generating algebras for which we do get 1 here. But then the tricky part is sort of moving beyond these cases and showing it holds in general. I guess one other thing to point out is given this 5 here, if it generates the hyperfinite 2-1 factor, then that's diffuse. So you already know that such an A will have free Stein dimension at least 1. So you really only have to show that it's at most 1 if you wanted to prove such a thing. And you know, why? Okay, let's say you prove this. What does this gain you? Well, in particular, what you get out of this is that if you had a 1 cocycle, beta, on some discrete ICC amenable group, then this conjecture would tell you that it's necessarily bounded. And so far, the only proofs that the only way that anyone knows how to show this currently is using these L2 Betty numbers. But if you're able to show this sort of in this algebraic generality beyond this group case, then necessarily your proof would have to sort of skirt around these L2 Betty numbers. So that's one reason why you might care about such a conjecture. Okay, and yeah, let me say one last example where I guess we get this quantity here. This was suggested to Ian and I by Vaughan Jones. So thanks to him. So say you've got U and V are Haar unitaries. So this just means that all of their non-trivial moments are 0. And that they satisfy the following commutation relation. E to the I pi theta, 2 pi. So where does this show up? If you look at the C-star algebra generated by these unitaries, you get what's called the a rotation algebra. And particularly interesting is when this theta is irrational. In that case, you get that this thing has a unique trace. So then you can ask what the free Stein dimension is for the algebra generated by these unitaries with respect to this unique trace. And well, it turns out you always get 1. In particular, you lose sight of this parameter theta. Okay? So from a C-star algebra perspective, that's bad. You would like this thing, if this was a good C-star algebra invariant, you would like it to at least remember this value theta, but we lose it here. But the upshot is that if you look at the von Neumann algebra generated by these, well, you get the hyperfinite 2-1 factor. So in fact, this is just more evidence for this conjecture. All right, I'll stop there. Thank you.
Any questions for Brent?
So the closest we can get to that, so no is the short answer, but we have theorems where we can show certain analytic elements can be sort of added to the algebra without increasing the free Stein dimension. And this has to do with elements that live in the domain of the closure of the free cyclic gradients. So we can increase the algebra by certain elements and not increase the free Stein dimension, but this is a long way from saying that you could throw in arbitrary elements in the von Neumann algebra and not increase the dimension.
Any other questions?
Sorry, this question's a little silly, but in your laundry list of properties about things you know about the free Stein dimension, you always compute it for an algebra, which then generates a von Neumann algebra instead of on the von Neumann algebra itself, and I don't know why.
So when you consider derivations that are defined on the entire von Neumann algebra, they are automatically bounded and inner. So you don't get interesting derivations there. You want derivations that are defined on some weakly dense subset, and then these can in particular get you unbounded ones. We do have a way to turn the invariants for the algebras into some invariants for the von Neumann algebras by like taking soups overall generating algebras. And you would expect these to be mostly incomputable, and that's true, except for some very special von Neumann algebras, things with like property T or L2 rigidity. So very strong rigidity properties, you can still compute it and you get 1. But,
Any other questions?
I have a question about the square on that trace. So it sounds like you're taking the subspace and thinking of matrices and counting how many entries are in there somehow. Could you say why you squared it?
well, here's a cheap answer. This is equal to. I mean, you can get a more interesting. So, like, let's say you look at the A is the n by n matrices, and then you look at the A central vectors in A tensor A. This is something like EIJ tensor EJI, where you sum over I, things that look like this. In fact, that should, up to normalization, give you a projection onto some subspace of the central vectors. So there you're going to get, product of 1 over n. That's why it shows up in that case.
Yeah.
So for the calculation on the rotation algebra,
So what we can say and what we use to compute this is that if you have some unitary that normalizes your algebra, and let's say your algebra contains some self-adjoint operator that's diffuse, then the free Stein dimension you get by considering their join is at most the free Stein dimension of A. So this would only give you, if you attempted to do this for some group of unitaries that was acting on A, these would give you pretty crude estimates. And so the thing you want to see here is sort of like a Schreier formula for groups. You'd want like 1 over the size of the group. And right now we don't have quite that level of estimates here.
So let's thank Brent again.